Okay, good morning, everybody. Welcome to this WISE public lecture in conjunction with the Electrical and Computer Engineering Department. You can hear me, right? Okay. So, it's a pleasure to welcome here our guest. I guess Jay Liu is not right now, is parking the car, so he'll be joining us soon. But we have here Hong Cheng. Let me start with the territorial acknowledgement. The University of Waterloo acknowledges that much of our work takes place on the traditional territory of the neutral Anishinaabe and Haudenosaunee people. Okay, so you're an expert now. on our campus, our main campus is situated in the Halmina Tract, the land granted to the Six Nations that include 6 miles on each side of the Grand River. Our active work toward reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within the Office of Indigenous Relations. So with that, let me introduce our first speaker, Dr. Hong Cheng. She's a former student of mine, so it's a pleasure having you here, Hong. Thank you very much for coming and agreeing to deliver this lecture. She's a principal engineer at PGM. She's a well-known practitioner in electricity markets and power grid operations since she was a grad student, in fact, when she started this. Grid operation risk mitigation. In the past 2 decades, she led the development of many power grid control room applications which have achieved billions of dollars savings in energy markets. Following her passion for technology innovation, Dr. Chen also serves as an industry advisor for many R&D projects at National Science Foundation, the Department of Energy, and Power Systems Engineering Research Center. Dr. Chen is an IEEE fellow, so we're very proud of all her accomplishments. And by the way, she was recently made aware that she got the Wanda Reed Woman in Power Engineering Award. Congratulations, Hong. I guess it'll be delivered in Seattle in about a month. She has been actively leading IEEE PS technical activities at various capacities for the past decades. She obtained her bachelor's degrees in 1992 and master's degree in 1995 from Southeast University in China, and her PhD degree in 2002, that was a while ago, 20 years ago, from University of Waterloo in Canada. Congratulations, Hong, for your award, and thank you for being here. She's gonna be talking about. Do we have the presentation ready to go? Okay. Overview of electricity market operation. Thank you very much, Hong. The floor is yours. Thanks.
All right. Yeah, thank you, Claudio, for the introduction and for inviting me here. Thank you, Kanka and Salama. Great to be back to Waterloo campus. Very familiar campus with lots of new surprise, which I was not prepared for that. Okay. So for today's talk, I'm mainly focused on the overview of electricity market operation. So you know electricity market are functioning around the world. So I will mainly focus on the PJM market. Market have variations are everywhere, but the philosophy apply to all. So first, very quick introduction of PJM. Then I walk through the high-level wholesale electricity market, especially focus on integrated system market operation. There I touch upon some hot topics: uncertainty, renewable, storage, and distributed energy resources. Finally, I mentioned about the system operation under extreme weather. That's a very hot topic for these years. So first, PJM, very high level. Our system is a part of the Eastern Interconnection. So we have about 1,100 member companies. We serve 65 million people for the 13 states and the Washington, D.C. area. Our all-time peak load is over 165 gigawatts. And our current generation capacity is over 183 gigawatts for over 1,400 generation resources. So one thing is 21% of US DGP is produced in PJM region. So these slides here basically show you our annual billings for the past 10 years. As you can see here, for 2022, the annual billing is $86 billion, and for last year it was a little bit shy of $50 billion. So far, the wholesale electricity market operated by PJM is still the largest wholesale electricity market in the world. So this slide showed the PJM fuel mix. The graph on the left shows our current existing capacity mix. As you can see here, the gas unit, gas fuel type is our current dominant fuel, close to 50%. Then we have about 20% coal and 20% nuclear. So currently, renewable still, no percentage is still quite small, less than 10%. So the graph on the right shows our queued generation capacity mix. So that's in our current queue. It's about 2,000 gigawatt queued resources. About 95% of current queued resources are renewables, and about 50% are solar, solar and hybrid. So the queued, they are already submit interconnection studies, so they are planned to interconnect to our system, but may not necessary to be in there. All right, okay. Okay.
Yeah. Sorry for the interruption, because we have people online. So we are going to leave the questions for the end of the presentation, so you can use the microphone so people can hear you online. Okay, thank you.
Okay, yeah, sure. Should go. All right. Now, very high level wholesale electricity market. So this figure basically shows the high level multi-settlement market design. So multi-settlement market design has been followed, especially in the North America. It's a mainstream market design. So as you can see here, the time frame ranging from planning horizon to real-time system operation. So when the time closer to real time, the uncertainty really goes to much lower level. So from planning horizon, we have the capacity market. At the PJM, we call the reliability pricing model. So that capacity market trying to address resource adequacy issue, making sure the future system is reliable. Some of the market regions don't have the capacity market, but they do have the reserve adequacy program to make sure the future system reliability. Then approaching every operating day, there is a day-ahead market. So day-ahead market is a financial market cleared based on bidding demand. So once the day-ahead market closed, then we have all the megawatt schedule and the pricing are the binding financial commitment obligation to all the participants. So currently, our day-ahead market clear about majority of a resource for the operating day. But as I mentioned, the day-ahead market is a financial market. It cannot guarantee they can cover everything needed for the physical power system operation. Then we have this reliability assessment commitment process. That process basically bridging the day-ahead financial market with physical power system operation. That process trying to evaluate now based on the forecast load for the next operating day. Do I have enough generation to meet the forecast load? If there's not enough, then we will call additional slow start unit, mainly steam unit, could be combined cycle, called before the operating day so they can prepare to come online for the next operating day. Then in the real time, we have the hourly unit commitment process, basically looking ahead 2 to 3 hours ahead, committing we call the fast start unit. They are basically combustion turbines to commit them to based on the real-time forecast load. And then we have the real-time market, which is cleared every 5 minutes. Basically, if every 5 minutes send a dispatch signal to all the resources, it's mainly generation resources to meet forecast load, as well as all the reserve requirement. So now we have all the energy co-optimized with all the reserve product in real time and also in day ahead. Then the focus is basically it's physical real-time operation. That's the focus. We have the AGC, so basically have 4 seconds to fine-tuning regulation resources to fine-tuning to meet for the frequency regulation. Then on the after fact at the PJM, we also have perfect dispatch, which is after fact process to bring feedback knowledge back to the operators to improve the operation. So that's When I mentioned, when I go to the timeline from planning to real time, when the coupling become more tighter when we go to the real time. So that's why I'm mentioning here, it's mainly on the day ahead and the real time. So the slides here show you the day ahead market operation. It is a financial market. So as you can see here, the participants have we have physical bid, which is gen load transactions. The physical own the facility. Then we also have the virtuals, Inc, DAC, and the virtual transactions. They are purely financial players. They don't own any resources. So they are part of the day-ahead market as well. And then regarding to the system topology, it's mainly come from the transmission outage schedules. Based on the outage schedule, we know what's the next day's system topology. Well, the clear day-ahead market correspondingly. So for the day-ahead market clearing, two main parts. One is unit scheduling dispatch. So in the SCAD process, then the feasibility analysis, trying to make sure the cleared schedule, they are physically deliverable in the system. And this slide shows the real-time operation. If you recall, the previous day-ahead operation, very similar. But the big difference here is in real-time operation, there is no virtual. So everything is physical. So in real time, we have generators. They are dispatched to meet the forecast load, as well as interchange schedules. In this case, SCAD is main clearing engine for the real-time market clearing. For state estimator is the one basically provide the input to SCAD. What's the current system conditions? What's the generation stat and load status? And then we also have contingency analysis provide constraint sensitivities to SCAD. So one thing I want to mention here, ideally those should be enough. Everything can be automated, but it is not right now. We have dispatch actions. So not only in order to mitigate the uncertainties, also because of the current limitation of all our tools. So dispatch action is still a very important part of the real-time dispatch. So they are the one, for example, they can anticipate the load forecast may not be accurate, hydro unit can come on and offline. They can fine-tune the solution, set the scenario for the real-time dispatch, maintain the power balance every second. So this one I'll quickly go through. So SCAD is the core engine for both day ahead and the real time. So they basically mathematical optimization models to either we say minimize total production cost or maximize social benefit. The constraint-wise, you can see here we have power balance, transmission constraint, reserve requirement constraint, as well as resource constraint-wise. So this is a very typical, very standard, basically across all the markets in the world. And then most of the market currently co-optimize energy and reserve. In that case, when the market cleared, not only energy megawatt and the locational marginal price, there is also the reserve megawatt and the reserve clearing price as a part of the market clearing. So next, I'll talk about integrated system and market operation. That's my favorite part. So as you can see here, okay, this graph a little bit cut off. So the objective of market operation is market efficiency. We want to know more as efficient as possible. And the system operation objective is trying to we have to mitigate operation risk. So these two objectives often they have very opposite impact on generation scheduling. If I want to be efficient, I want to be commit as just enough generation. But if I want to be mitigate the risk, I would commit more, but that will be hurt the economic efficiency. So in this case, often have very opposite objective. The ideal situation, we want to be market equilibrium. So consider both objective. So that's the ideal situation. So if we are going to the system operation, right now, all the operation criteria, for example, the operation criteria set by the NERC, they are the criteria for system operation. Whenever it's possible, these operation criteria are formulated as a market operation constraint. In that case, these constraints are included as a market optimization, market process. So in that case, once market cleared, all the signals, price signals, basically reflect the system operating condition. When these signals sent to a market participant, generators, load, neighboring RTOs, they responding to the price signal, they will also help to address system operational conditions, help to enforce system reliability. So that's a very ideal situation. However, I said there is current software tool limitation. Not all the operation constraints right now we can incorporate as a constraint in market operation. So if you can see the downward here, so right now for every market, there is still amount of vary by different market. There is out of market actions. Basically, those out of market actions purely are the operator action decision. They are not going through the market. They directly send we say dispatch instruction or signal to the resources, trying to maintain system reliability if market signal is not enough to do so. So our goal always, we're trying to use all the markets to reinforce system reliability. One of the key examples, for example, the fundamental locational marginal pricing is we're using market signal to relieve transmission congestion. Another example is reserve and the reserve market. At the beginning, reserves are very important for system operation. They are there, always there to hedge the operation risk. Reserves are across different time frame. We have 10-minute synchronized reserve, primary reserve, or the 30 minutes, we say the secondary reserve. At the beginning, there is no market for reserve yet. So basically, pure energy only market. In that case, the pricing signal does not reflect the system when system need those operating reserve requirements. So for the past, within past 10 years, all the markets starting all have this reserve market created. The idea is trying to use a reserve price signal, send a very transparent price signal to encourage generators to maintain their flexibility to help system maintain reliability. So as of right now, for example, at the PJM, from day ahead to all the way to the real time, we have energy co-optimized with all these reserve products. So in that case, the price signal, reserve price signal reflect what dispatch the needs to operate the system reliably. Some of the hot topics, when we talk about today, uncertainty, it's a very big topic in the system operation. It has always been there. No matter how well systems are well designed, planned, always have uncertainty. The generation tripping, system component failure, they're always there since day one of we have the power grid. Then on the load side, the load can change, especially for the recent years when we have more and more distributed energy resources on the load side. So now load become more volatile than before. And also we have the interchange volatility. Those are the activities across the boundary of control centers. For example, PJM with MISO, PJM with New York. They are very volatile, really depend on the pricing difference across different markets. So one day, within 5 minutes, the change could be 7,000 and in and out. So those are the really big challenge as well. And I mentioned currently PJM system, we have about close to 50% resource are gas resources. So for the past decade, we're seeing the gas uncertainty will become a big issue, especially during the winter extreme cold weather time, because the generators are competing with the residential customers for the gas, for the heating. So that's become a big topic for the past 10 years. Then of course, renewables, renewable resources, wind, solar, they are naturally volatile. So those are the challenge, really posing to the system operation uncertainty. So right now, our market software, we don't have this market software which can stochastically consider all these uncertainties in the market clearing. So right now, what we have multiple small and fast software. They are staged for different level of uncertainty to help operators hedge operation risk. Especially in our system, we have lots of, we say, fast data resources. they can come on very quickly, their gas resource. So if we are considering all the uncertainty before the operating the day, they could be overkill, especially system conditions can change. Uncertainty going to really much lower level when we go to the real-time operation. So we have that luxury, basically, wait and see, based on system condition change, then fine-tune and adjust the system commitment within the operating day. So again, here you will see the day-ahead market, they are currently closed at 13:30 for the next operating day. They are basically positioned about 90% of our generation resources for the next operating day. Then I mentioned earlier, we have this rack process between 30:30 and 14:15. That is a rebidding period, rack trying to base on the information. During that time, for the units which did not clear the day-ahead market, they can adjust their bid. Then at 13:15, rack process going to evaluate based on forecast loads instead of like a day-ahead is a bidding load, committed resources correspondingly. Then we have the CT optimizer, which is running at the beginning of our operating day, provide a whole day, 24 hours operating plan for those fast start units. This is one thing is as a plan, so the operators have the plan in their mind for the operating day to start with. And also for some of the gas units, if they are taking a little bit longer time to start, they can call them early ahead. So that's the two main purpose of the CTO. Then in the real time, we have this IT SCAD. It look at the 2 hours running every 5 minutes, provide the unit commitment and a decommitment recommendation to dispatchers. So dispatch will commit the resources correspondingly. Then we have the RT SCAD, basically purely dispatch software. It's a real-time secure constrained economic dispatch. So sending every 5 minutes, sending dispatch signal to all the generators. All this real-time application from rack to the RT SCAD, they all have multiple scenarios for the operator to choose from. Then I mentioned earlier, dispatch action is important because they are the one to run all these softwares, making decisions, setting scenarios. So we have at PJM, we have Perfect Dispatch, basically using previous operating days experience to guide the dispatch, to help them to set the scenario needed for the operation. Now back to we have, as you can see the slides early. Now gas is our dominant field, but if you see the interconnection queue, 95% are renewable resources. So renewable really, it's the one really over the across the whole industry, we are all trying to accelerate renewable integration to combat the climate goal. So from system operator perspective, I'll mention these 4 challenges here. So number 1 is variability uncertainties. As I mentioned, wind and solar naturally variable and uncertainty, but they are posing the challenge to the operators. They are used to this. We are dealing with dispatchable generator for a long time. So that's one challenge facing to the operation. The other one is inverter-based resources, right? So wind and solar storage, they are all IBR resources. And system operators have been dealing with synchronous machines for the past 100 years, so not quite used to that. And also the adequate modeling, the IBR, when we have more and more IBR resources in the system inertia decrease, and also we have less system flexibility, ramping capability, and not even mention the protection challenges. So the adequate modeling and the study of IBR resources at the transmission and distribution level is an ongoing challenge to all system operators. And also system operators don't have enough information about the IBR's operation characteristics. So now right now, NERC is basically working on the reliability criteria to address IBR resources. The third one is resource adequacy. Now load is increasing rapidly because of electrification, because of data center load, and also traditional units are being retired. So it has been retired across the past years, and for up to 2030, we are looking to retire up to 60 gigawatt of generators. So, and a new generation addition, not keeping up with the retirement, If you see the early slides, we have about 200 gigawatt interconnection queue, but not everything can come online that quickly to meet the load growth. So the long-term wise, we really meet the challenge of reserve adequacy. We need the fourth one is market design. We need a market signal to incentivize the investment. And all this, when we have more and more renewable resources coming online in the system, these renewable resources, they are basically zero marginal cost resources. So because of that, really now the energy revenue, they are decreasing, just not enough to keep the revenue adequate. So in that case, how do we reform the market, make sure we have strong market signal to invest in new investment generator have more flexibility to hedge the volatility. Also, long-term wise, hedge, make sure attract all the new generation investment, reflect the changing system mix. Those are the challenges, in my point of view. We have to address these challenges to fully leverage the renewables potential. So I'll use the power balance basically as an example to illustrate here. So as a grid operator, balance general load is our main responsibility. So on the load side, net load ramp is increasing. So basically we see increased load ramp, especially DERs. On the gen side, we have because of generation retirement, we have the decreased available operating reserve, dispatch resources. So the graph on the right, you can see net load ramping. Our current system is about 20 gigawatt for 3 hours. The graph on the top left shows our current scheduled reserve available in the system. The blue ones are the total, and the green one without gas. So basically, you can see that gas unit provide the majority of the scheduled reserve right now. So right now, we have enough scheduling generation flexibility to meet the load ramp. But in the future, it will be more challenging. And the lower right, lower graph basically showed April 4th, the solar eclipse we just experienced on April 8th. We survived. We have no problem for that event. The total generation impact from behind meter, from meter, it's about 11 gigawatts. With our current system, not a problem at all. We forecast, we plan for that. But in the future, when we have more and more renewables, solar eclipse, especially full eclipse, will have significant impact, a challenge to system operation. So opportunity here, what can we do with that? We have to integrate a significant amount of clean energy resources as fast as possible. Wind, solar, hydro, and we also need clean firm generators. For example, advanced nuclear to basically compensate the volatility from the wind, solar, those intermittent resources. We also need lots of flexibility to hedge that. So storage really is like a silver bullet for the system operator to provide the flexibility. They can really make all the renewables reach their full potential so that we can access the electricity from the solar when the sun is not shining. So really solar, I put on the storage, I put both on the gen side and from the load side. And equally important, we need a lot of flexibility from the load side. So virtual power plant is really taking off for these years. They are the one operator make sure we have all these flexible resources available when system needed. Actually, for the past couple of extreme events, the demand response, or we say low side flexibility, really saved the system, make us make system reliable, avoid the rolling blackout. So very quickly, because of timing, so I will now show up. Those are the storage technology currently in PJM. We have the largest pumped storage resource in this world. All these recent years, we have advanced storage technology as well, flywheels, batteries, EV, and thermal storage. And these slides basically show you current storage resources, how they are participating in the market, from capacity market all the way to real time, especially for advanced storage, because right now they are not that long duration, don't have lots of sustainable energy yet. So in that case, they are mainly a participant in the fast frequency market. And you can see here, the currently DERs, we have about 3 gigawatts participate in the wholesale market. And then we have more than 10 gigawatts. They are behind meter. We say behind meter, basically, in that case, they are reflecting our load. Very quickly, extreme weather. That's one of the biggest challenges we have right now. As you know, with the climate change, we have more and more extreme weather than before. Extremely cold, especially one challenge, especially our current system have significant amount of a gas unit are made as a dominant field. So this very quickly go over our Winter Storm Elliott example. You can see here that's happened in 2022 holiday during Christmas time. Those are for the 10 years from December to the January all the way, all these periods load. You can see that for the 2022 Christmas load is definitely an outlier. So next slides basically show you, zoom in for the details, just to see the load from December 23rd to 26th for the past 10 years. You can see that for 2022, even for the valley, it's about 40,000 megawatt higher than the previous years. Now, for the system operator, valley is very important. Valley is the time, the pump storage, we can prepare generation to meet the next day's morning peak. So for that day, we have such high valley load. Our pump storage even did not have the opportunity to pumping because we are barely trying to maintain system reliability at that evening moment. So really, it's a very challenging, a very nerve-wracking during those days. And then here, you can see the challenge we have. On the load side, we under-forecasted. The graph on the left is for December 23rd, and the right is December 24th. We under-forecast about 10%. So we did not prepare for that. It is not just PJM. It's for all the East ISO. Every RTO under-forecast loads. Because we know there's not enough historic load to indicate such high load during those days. And what happened on the generation side? The highest is December 24th, around 7 o'clock. You can see we have over 40,000 gigawatt of generation out. And 70% are gas unit. So this is really, finally, we have called the demand response and also public field for conservation. So we did not have to shed any load. We survived. Basically, there's no problem. But looking to future, we are prepared planning for the next extreme weather. How do we forecast load better, especially for the extreme weather load forecast, which don't have lots of historic data for that. How do we better align gas with electricity market day, mitigate, provide more gas certainty, especially that time we are the weekend going to the Monday. So during the weekend, gas, there's no, if they need the gas, they need to nominate ahead of time. So we are currently trying to working on, we have multi-day forecast, a multi-day unit commitment, trying to provide more certainty to the gas unit so they can procure gas ahead of time. So this is work undergoing right now. We are working on that. And of course, we're trying to address, improve our capacity market, provide a better signal to incentivize generation availability during extreme weather conditions. So this is my last slide. So my last words here, so basically, we need a significant increase, accelerate renewable generation, but reliably. So we need to work together on that. So we integrate renewable while keeping the lights on. So that's all from me. Thank you.
Thank you very much. Yeah, I would like to open, although we are short of time, we'd like to open the floor for a couple of questions. Hi, Jay. No, we'll have first the questions because they are different, not related presentations, and then we'll move on to Jay, if that's okay. Any questions before we actually forget the presentation? Magdi, just a second.
Oh, I want the mic. Okay, sure, yeah. Just want to ask you about the extreme weather condition now. When you say about extreme weather condition, about the forecasting of the extreme weather condition, like what do you expect, like to know from that particular moment? Like what are the output data that you need for that extreme weather condition? Is it generation? Is it load? Is it what? Like what are the like say parameters that you want to get out of this?
Yeah, so to prepare for extreme weather condition on the load forecasting wise, we would, instead of using past 10 years, we will ask, because trying to access more extreme weather condition, we are going back to even further, to 1970, to digging out those extreme weather days. That's on the improving load forecast date. And also for generation-wise, we need to know, because a lot of our generation are the gas unit, we need to know if they have enough gas, or are their gas already be procured? Do they have outage or not? If no outage, then do they have the fuel issue? Basically, we need to make sure they have the energy assurance, not just no generators available, but no gas. And also the other thing, big thing, coming from extreme weather conditions, make sure all the generators, they are winterized. So they are able to run under extreme cold weather conditions. And then we will the third one, we make sure we have enough demand response available. When the time we need to call demand response, we have during those time, we have over 10,000 megawatt demand response. So they are the one finally, relying on their help, we system to maintain the reliability. So from load, from gen, and from demand response, yeah.
Thank you.
So I
Yeah.
have one question.
Yeah.
So regarding the capacity market, which you said, so just if you could elaborate a little bit more on the capacity market. So does it also include the demand response contracts? And also there has been a trend of including the interchanges. So what about that?
Right.
Are they also captured in the capacity markets?
Yes, so currently our capacity market is looking at 3 years ahead. So we have those existing generators, they can bid into the capacity market. New generators, basically the new generators, they're not there yet, they can bid in. You mentioned, yes, demand response, they are participating in the capacity market. Actually, capacity market is one of the main revenue stream for demand response. Demand response, even energy efficiency. Of course, energy efficiency right now is kind of a controversial topic. And also interchange, we will rely on, there's interchange, certain amount of interchange considered in the capacity market based on the forecast, the peak load, and also reserve margin we are procuring, yeah.
Well, thank you very much, Hong. I guess we run out of time, but very interesting presentation. I have a lot of questions, so over lunch I will be asking. He has a microphone.
Okay, all right.
So I'll be asking you a few questions. So with that said, let me introduce Dr. Jay Liu. He's currently a VP of Transmission at Exus Renewables, NA. At Exus, he oversees renewable energy resources, grid integration, operation, and transmission services. Prior to joining Exus, which I understand was recent, he worked at PJM and ISO New England in energy infrastructure development and operation. Jay has been engaging in grid transformation into sustainable and resilient energy infrastructures in the past 3 decades, with an industry record of adding more than 28 gigawatts of generation resources and 2,000 plus transmission projects in service into the power grid globally. Jay holds a PhD degree from University of Waterloo. He's a former student out of Magdi Salama. He also worked with us. So we are very proud of all his accomplishments. Thank you, Jay, for coming here. And an MBA degree in 2009 from Penn State University, a master's 1997, and bachelor's 1992 degrees from Power Systems in Southeast University, China. Thank you, Jay, for being here. The floor is yours.
Absolutely. Thank you. Thank you, Claudia. Appreciate it. Yeah, well, as Claudia just said, this is a very important moment for me. I'm not just a driver for Hong to drive all the way back to Waterloo. This is also my 20 years anniversary for my convocation of my PhD degree. So, thank you so much. It's very proud. Hong and I were back to our lab yesterday afternoon at Highwatch Lab. From the first floor to the second floor, I see the doors. I see, oh my God, the chair is still there.
But the lab is missing.
Highwatch Lab, the chair is still there. It's my lab. Yes, Hong's, your lab, probably moved. But we still find the room. We not only find the room, Claudia, your lab, your superpower computer there, but also the physical, lab, which Hong and I used debate and argument, okay, about technical topics. So before I go to my slides, I know the time is limited. I don't want to make too much time on your precious, research time here.
Presentation.
Yeah, but let's stay with this one because I disagree with her a little bit. So everything Hong said is great. okay, and since I've been doing this many, many years in the work and in the market, I see some of the graduate students here. Quick question. Is the energy market is for energy or for power?
Nowadays, both, yeah.
Nowadays it's both at the beginning part when we design energy market. When Bill Hogan and Andy Yao, these tools in the bunker room, try to figure out the original problem is a power problem. And that's still the fundamental power problem today in the core engine. You use a power flow, put energy from the market information there, called the SCADs now, to solve a power balance in terms of constraints, economics and reliability. That things being patched because so many challenges after 20-something, 30-something years, after some failures, after some success, we are trying to provide a market signal. My brain only 6 months in the renewable energy developer side. But I can see the gap now. That's the message I'm bringing today back to the campus. What is the transforming change? Do we need to see the infrastructure transforming change? Or are we saying that we're not only look into power balance? Maggie did the load forecasting paper many years ago, have ANN model developer, right? Try to solve uncertainties. But you can hear from home, from PJM control room, we are trying to do what? We're trying to say, hey, you respond better. Hey, you got your gas better. Hey, you do your forecasting better. But we're not solving a fundamental need. The need is from our load. I want energy at a certain time. So they talk about delivery adequacies, talk about investment adequacies for long run. So all these challenges are good. All these challenges, there's one person in the world actually actively try to solve it because it is very, very profitable for him. He also sent SpaceX to the sky. He also built that beautiful Tesla car. But that gentleman today is announcing his company is an energy company, not a power company. By what? By developing energy storage distributedly into the cars. By power a lot of GPUs in his buildings in the next 2 years, not only for automatic driving, but also trying to provide a lot of controls, predicting people's behavior, energy consumptions, and also using his Megapack powers as a standalone stationary power supply energy storage, long duration, 4 hours. I'm building 3 of them now in the US, trying to do what? Fix these uncertainties. With a fee, with a heavy fee, the market design is still based upon the power, fundamentally. The deficiencies, the defects, all these things, sensitivities from Jacobians are what? Power. When we multiply by a time scale, are we going to have a different equations? So those are the questions I had all the years at PJM myself, now at energy storage development and the renewable developer. I also see these questions because that come to me as my revenue for this year, for the next 10 years, for the next 25 years. All right? So let me just, okay, thank you. So as I said, I'm not going to come back to argue with my known longtime friend and colleague and wife, right, regarding how power market design should definitely on top of these topics. I'm just talking about it from a different view. I want to share with the room with all these genius, researchers and the students here about what is the transformation. If I heard the weather change is not resilient anymore, more and more new renewables is potentially be sustainable for environmental perspective, but the power grid is not sustainable, can be crashed if you do not forecast them correctly, right? So what is going to be changing now? What is and we use the word term called transformation. You go to IEEE general meetings, you're going to see me and Hong in July, and most of you, hopefully. Transformation is a big topic there, big term, very popular now. 5 years ago was a working group, small task force with standard association. Now everybody talks transformation. So what is transformation? What are we transforming? Where is our destination? And how can we be prepared for that? The slides is pretty much in more detailed words. You can read it because of time. I will go very fast here. So as a power engineer, after graduating from Waterloo, I was not able to be the postdoc and be the academia side, unfortunately, for that my year. So I went back to industry. I stayed there for 20-something years. The 4 terms I often heard are power system planning. I was in the operation market for a very short while, a long time in the planning side. Planning for about 5 years. Immediate need at just 3 years. Backbone development. Very proudly, I built the most backbones in the East Coast as a project manager. But normally, a backbone project, 500 kV project, you take 7 years. It's the fastest project ever. You almost got the 3.5 years in US, but did not work. So aging infrastructure replacement. One time I went back to West Virginia, and the AEP planner, planning director showed me, hey, Jay, look at that tower we need to replace. Okay, cool. It's 55 years old. Great. I don't know how to come up there with my crane right now. I don't even know people 3 generation before they were able to build that tower, but right now we don't know. So I had to change the design, find a different route. Aging infrastructure can be 50, 60 years old. That means our infrastructure put it today, would that be stay there for 30, 40, 50 years later on? Power system hardening. One bad event happened, natural disaster occurred. We find out the weakness of our system. And we fix what? The weakest link. When I was at the campus here, watching TV sometimes, I saw that was the TV program, the weakest link. You find the weakest link, you fix it. You make that stronger. That's a short-term solution. So all these terms come back. What we heard is one big thing: long constant, time constant for power infrastructure. Compared to power electronics, compared to VLSI design, compared to electrical computer engineering, the Moore's law, we're talking about decades of an infrastructure change. Should that be right? Are we able to survive? We talk about long-time investment and the heavy capital cost for this. We talk about billions of dollars investment. And long return. As ratepayers, we pay bill. We ratepayers, we don't know how much we pay back to utilities for them to put a $1 billion of Hydro One work through our bill. So long time period, long time constant, and long time operation life. So all these things come back to this word for me: passive, expensive, inflexible, and heavily regulated dependent. This is the nature of the physics world we are working with. Good or bad? There's only one exception in China. They're different. But we cannot use that as a role model in the other part of the world. So if we talk about the power grid transformation, I checked the co-pilot. I don't know University of Waterloo whether allow you guys to use ChatGPT, do your research, but at least we can use that to learn something we don't know, right? At least in the casual way. So I did that last night. I say, hey, co-pilot, what is the transformation your view? The keywords, I agree with him. They talk about a complete change. If you don't want to change, you may end up seeing Elon Musk take over the distribution business very soon. Dial your thermostats and earn a lot of money for the campus power supply efficiencies. Or talk about a configuration change. Or talk about a shift from one direction to the other one with a success. So next couple slides, I will be, how much time I have, by the way? 2 minutes?
About 15 minutes or so.
Okay. So I don't know the answer. I'm only one engineer. 2 years, 3 years ago, I was still at a PGM. So I was able to do with IEEE, I did a global power grid operator survey. I asked the same question. Hey, what you are doing? What's your focus? You do renewable, You do a grid expansion, you know the passive thing of the existing legacy system, you notice something is changing, and you see the commutators, right, from the other part section of the business. What's your focus? So, is there a pointer? Anyway, okay. So we find out a very interesting few things from the high level here, okay? Energy storage. Most of the system operators say, I want a energy storage, strategies to be developed in the near term. I look into the demand response because I see the uncertainties, and I look into the distributed generation, and also I want to make sure microgrid and wind, all these things are able to be ready to solve my near-term problem. At the business side, they spend quite a bit of strategy for long-term planning, and very interestingly, frequency and the voltage regulation still a top technical challenge or concern by grid operators. So how to link this topic? I feel that was very well developed in theory, but still a top topic, top mind, in their, uppermost challenge these days. And some of the climate change things surface up. So one conclusion I got from this report with IEEE is, there's no concrete consensus among the operators, which the top three. It's diversified focus. But also somehow there are clusters of the studies here are balance of power and try to move into more like a service part. Why the service part, our load need energy, also power, need the quality, need the reliability, need the resiliencies, okay? So these are the topics we find out are a common challenge, but also a little bit diversified. So here are a few topics in IEEE, and through the work, we feel that, I believe, at least myself, in the grid transformation side will change some fundamental things change in our power infrastructure. Not only generation, the wired part, but also generation included. The very first part is the next generation fax devices. Especially Europe and China and Japan, fax devices still a very hot and heavy invested technologies. They're trying to make high power density, smaller size, lower cost. Very high voltage, ultra high voltage AC, like 1,000 kilovolts, is the backbone now in China. It's amazing. But in the US side, 765 kV, 500 kV, some HVDC circuits have been proposed, have been built. The current administration of US trying to make a massive backbone work, hopefully in the next 20 years. Hopefully they will be successful. Some technologies there are heavily needed to change the landscape of a power system. DC circuit breaker, and look at the MACD, remember the DC switch, okay? Well, we still keep the world record, by the way, for them, the power. Nobody do that, but that's the reason. But without a DC circuit breaker, we're not able to build offshore grid for HVDC grid for multi-terminal, much more dependable thing. You look at the papers, you look at Asia, China has some multi-terminal demonstrated. In Europe, Germany, and the offshore grid, they have a power multi-terminal TNET projects trying to be in service at the end of this year. Will that be dependable? Use a reference case. This is a material size. UPFC, the very first one, where is that? AEP, Ohio, 1999. Unfortunately, I caught that retire myself in PJM. Why? Because that technology, idea is great, material is not dependable for maintenance. So our challenges for us to overcome this. DC breaker standard coming out 2030. We're looking for 20 gigawatts interconnection by 2030. How? Without a DC breaker, how you can have to be radio in. If you radio in, you're not called the transformation in the offshore grid part. So those are the hot topics we're constantly watching, and we'll be able to enjoy their breakthroughs, all right? HVDC and hybrid DC AC, digital transmission substation. These two things are very, very important topics and invested by companies trying to break the gap. One thing, in the Western societies and US, Canada, I believe also included, and Europe, transmission line capability are constrained by not by the conductor, it's by the right-of-way. It's very hard to find the right-of-way, 200 feet wider to go through to build a massive transmission line. You go into the QEW, you go through that 403, you will see, oh, I have so many transmission lines there. How many lines per tower? Normally you see. In Canada, I was impressed, 2. Sometimes you have 3 conductors, 3 phases, right? The limitation is a high voltage lab job, trying to find out, do I have a good insulator? Do I have the good design for this tower? You go to Germany, you can see 3 or 4 lines per tower is common for some area. But you go to US, 1. Again, we'll be back to the long time constant, the legacy feeling, and technology standard. So these things, if we can improve them, that will change the landscape. If you increase your ask a home one day, so do a simulation. If I tell you my line rating can be increased by 10%, how many percent of the PJM market constraints can be resolved? Magically disappear. 90%. Even more than that. So we are patching to a power delivery problem with a lot of technical constraints with a very thin technical barrier. 10% of rating increase, 90% of congestion going away. Energy storage as a transmission distribution services, operating our system from the reliability preventive method, N-1, N-2, to something called predictive, economical, and sustainable energy service. And people ask me, Jay, you make just a term, you just make up one, right, last night? No. We are actually working in that word right now. I signed a PPA, power purchase agreement, with Meta, their data center in New Mexico. I don't really care the market. I signed that one. I deliver energy. He pay me energy. In day-ahead market, like the PJM situation, day-ahead market, more than 85% of the bids are much wrong. Bilateral transactions. So how efficient the patching, the market design versus the future energy service business model is something questionable, and we have to look into details, say, hey, where is the breakup we can work on? I try to fly into the next couple of slides. Slides are pretty abundant in content. I want to bring that some attention to the colleagues here, that there are some regulatory changes right now in the US are actually directing us to see a transformation. Our regulatory in the US, like FERC specifically, they issued 2 orders. These 2 orders are more important than the FERC Order 888 for energy market, and also more important than FERC Order 1000 for competitive transmission planning. These orders are enabling a breakthrough of the future. Order 1920, just issued about a couple weeks ago. This is order we call the landmark order. Why? The first time a regulatory at the federal level of the US directed 3 things. Number 1, you not only plan your power system near-term solutions for 5 years or conceptually 7, 8, 10 years. You do a 20 years ahead forecasting. How? We don't have the series there yet. You not only do the short-term load forecasting, you have to do the long-term, and you have to make that efficiency. It's a huge optimization problem, and the how is yet to be discovered. So look into these slides. I parsed out some keywords here. I don't want to go through the detail. It is an optimization problem for long-term solution, and we don't have the model. The entire industry in the US, regulatory side, us, RTOs, are trying to petition the filing to FERC, says, you tell me, you lawyers, what you want me to do, but you're leaders of the industry. Next week, we have a summit in DC to do that. The thing is how we determine a engineering model to solve a politics. But there's one thing in that order is very important. Very important thing is encouraging grade enhancing technologies. Do not hesitate to use them, utility companies. Use them whenever it's available. As long as it can help the system, use them. Never, ever in our industry, engineering in the history, a regulatory side, like a US body, encourage use technology when ready. So that opened a big door for researchers to commercialize your ideas, to work with engineers. Another order very important here is FERC Order 2023. This order is trying to help an issue. There are 3,000 people like me in the US right now, try to invest projects. And we together in the queue by the end of last year, we put about 1,570 gigawatt generation and 1,000 gigawatt storage. We try to integrate to the US power system. Conventionally, you have to study each of the requests and find the feasibility or not, okay, and do the implementation. But that process, one by one, queue the process, we got a success rate is about 14% of capacity, 20% of the total request, 14% capacity put in service. That's a statistic. Even that way, that method work, you're talking about 300 gigawatts new energy, 120 gigawatts energy storage to be in service by the end of 2030. Today's US power grid are not capable to handle this amount. So what happened? So we have to enhance the power system. We have to determine how to connect it economically. Order 2023 is to define a process to let everybody able to go through this computation and find out the lucky 14%. RTOs are doing this work. You can see some trend, how this renewable energy integration causes requests going higher, and how these things are not going to use the traditional way for the study part. Power flow will not solve this easily. We had to find artificial intelligence. And the previous PJM market designer, Andy Yao, he left the PJM, joined Google, he tried to solve this problem. This is an optimization problem using artificial intelligence. I skip these slides here. We talk about something about DC circuits. So I want to show you why the offshore grid is very important, but we are not able to implement it today. 5-6 years ago, I started doing the offshore interconnection in New Jersey. I put the bids in RFP order there. I was suggesting the utilities and the manufacturers to build some kind of offshore grid so I can tie in this generation over there. A very simple offshore grid. They come back to me, including Siemens. They say, I don't know how to do it. So I have to go radio. And this US DOE slides, they think about radio as well. Some kind of a simple offshore grid in the long run, but near term, all radio. Now the question I asked the program manager, also my classmate in the college, I say, Dr. Fu, how are you going to tie into my onshore grid without harm? DOE will not come to a very comprehensive solution. We together have to find a way. Now with these new technologies, hopefully this will not be a burden. My last slide here. What is change to our load? The load forecasting, Maggie, you asked earlier, what you're missing, what you're having is for the conventional load model. We have a monster coming in our system right now. And this one, we never have a historical load model to support the conventional power. It's data center load. The condensed, they're talking about right now is about 9% of total load by APRI's estimation and the Goldman Sachs financial side as well, that by 2030, we're going to see 35 gigawatt data center load in US. About 90% of the total load. These loads actually are coming up. Their load profile is yet to be defined. Whether they will be power electronic way, are they right through some disturbances, is harder for the real-time control. So we're going to do some research work, and whether or not a renewable energy can directly supporting them, without cause this utility have to spend a $50 billion generate transmission investment. My company actually doing that. Very hard, but we are trying to find a different way, because we cannot wait. 2030 is only 6 years away. Transmission line built, either line built here, 7 years time constant. So we have to break that gap. We have to try to fill in that gap, break that ice wall. We try to find out a new solution. Very, very much engineering and technical advances we have to do, but we really enjoy the challenge. So my final words here, I want to share with the professors and the future stars here, graduate students here, is one word. We need to be prepared. We have no other choice. We are in this industry. We need to be prepared for the next generation power system, power grid. We need to reduce the time constant from research to practical application. Want to change our model, business model, reduce the time constant for commercialization, okay? And industry and academia collaborations, we need to be more and more coherent. We need the wisdom from this campus here to solve these future challenges. That concludes my talk.
Thank you. We have another microphone. It's not turning on. We run out of battery. Just a second. We have time for a couple of questions. Just a second, because we need the microphone because there are people online.
No problem. So that's another power problem.
Easy solvable.
I went to at Dallas. I went to the Mega Pack, building for Tesla's big building. A lot of robotics there, a lot of batteries, a lot of cars. The time,
All right,
amazing.
so thank you very much, Jay. Thank you for a very interesting presentation. Very thought-provoking. I appreciate that. Any questions from the audience? If not, I have a couple.
You go ahead first.
Okay, so I have one for you. I was reading an article in the New York Times about all these new technologies for transmission, new wires, new cables, that I wasn't aware of. And how much are you guys working on these technologies? So basically using the same right-of-ways and replacing, for example, the wires with these new
Very good question. I chaired the transmission substation committee at the PJM for the new standards, about 6-7 years before I left. So yeah, we constantly renew, changing these technologies, selections. There are like a carbon core, conductors, and that gentleman who developed that project going to be at the Great Edge next year. I have a panel there, going to invite him to talk. So those wires used to the tower, it's not because their technology is new. Ironically, it's because they're lighter. They can compare it to the conventional tower, composite core or carbon core conductors can carry much more power at the existing tower. So that reduces utility cost. That's the most motivation. When I ask the engineers, the planners, hey, why do you consider just different technologies, right? They say, Jay, I don't have money, time. I tear down a tower versus a reconductor. It's totally different budget, totally different cost. It's a very practical things, not necessarily technical advances, but they still have rooms to utilize this new technology.
But is there plans to develop these, to use this? Or?
Yeah, we already have projects using utilize them now. I can see more and more opportunities because we need to double the transmission conductor capabilities for most of the backbone, so 230 kV above transmission lines. So if we double them, it's not feasible to rebuild these towers. So we can only look into these conductors to find a way. Lighter conductor, higher transport capability.
Thank you.
Yeah.
Yeah. My question is about the role of the regulator in your vision. Transmission line transformation. What is the role of the regulator in that transformation?
Great question, Maddie. Everybody puzzling right now because once 4 weeks ago, then the order was out. They still not posted the entire 4,000 pages yet. They just put a summary and already made the entire pond vibrating like a bowling now. What the rule of regulator? They have to for the ratepayers, the general public's interest and the national security. That's their fundamental rule. This worst generation of this committee today, they took a non-precedent action for this 1920, encouraging technology implementations, encouraging long-term forecasting and planning, but they do not know how. So their role is a visionary role. They believe in that to solve the environmental problem, climate change, we have to think out of box. If Jay Liu cannot do it, he should retire and have the new generation engineers and to take over the boat. Why? Because we just do not have time to wait to have this change. So they decided, make that order out. When read it, go ahead, use it. Utility company used to say, oh, I have conventional way, I don't want to use the new technology. In this order, that's wrong. You have to use most available technologies. Gave them the room to try.
Yeah, when we finish, I'll tell you one of my experience with the regulator for the intertie, and we'll come to that one because it's very interesting with the regulator here in Canada. I'll share that with you.
Absolutely. Thank you.
Yeah.
Well,
Okay. Thank you very much.
Thank you very much. So there are some questions online.
Yeah, we have a question on.
Thank you. Now we have an audience over.
We have a question online for Jay first. So the question is from Ashu. How to know which new great edge technologies might come up for 20 years down horizon for planning?
Very good question. Who asked that question?
It's a
Yeah. I gave a big plot for that question. Yeah, this is one of the puzzles. So next week in the DC, I will make sure I ask a question as well. That is a double-edged sword, rule making. We do not know 20 years later what type of technology we will use, will available. But that also encouraging, we try to find one. Have you heard about a fiber optic power transmission? Have you think about microwave? Dr. Mansour is not here today, but in DC, but microwave power transmission by the satellite? When I was students with Dr. Mansour and the Magdi,
So you thought about superconducting material for
not only that, just the microwave transmission to the satellite and coming down to Earth to reduce that. So these things are in and out. We need to find a more dependent way. At the end of the day, we serve the need. We need to have an objective function, have to define our subject to part.
Okay, so we run out of time. There are a couple more questions online, so what we'll do is forward them to you. Sana, can we make sure of that? We have a recording of all of this, right? So we'll forward the questions
Absolutely,
to you
no problem.
and ask for your helping, to you, Hong, your helping answer them because we have
Okay.
exceeded our time by a bunch. But nevertheless, thank you very much to both of you. Thank you.
Thank you very much. My pleasure.
Thank you for your visit. So apologies for the audience. There is an exam going on right now, the DC 63. So that's part of the reason why the students are not here. So they're taking an exam right now. So, but thank you again. Thank you, Jay. Thank you, Hong, for this very interesting presentation. And I look forward to more questions, more interactions during the lecture.
Anytime, my son is just email.
Thank you.